Today's topic will cover the electromagnetic spectrum, and that is a continuous range of wavelengths and frequencies from radio waves at low frequencies and to gamma rays at the high frequency end. Below that, I have an example of what an electromagnetic spectrum would look like. There are several different electromagnetic spectrums out there, but they all have the same kind of form. At the top, we see wavelengths with the Greek letter lambda, and that just looks like an upside down Y. And that the units for lambda is meters. Or at the top, it gets smaller where we see the visible spectrum of color, and those are given in nanometers. And at the bottom, we have frequency, and that is given by the Greek letter nu, which looks almost like a V, and that is units of hertz. So we'll get more into wavelength and frequency. I'll move on to the next slide. So wavelength is the distance between successive peaks, and the units again are given in meters. I've highlighted here on this example of a wavelength. This red arrow here is an example of what a wavelength would be, which is the distance between this peak and this peak. So that distance will give us wavelength. Then frequency is the number of wave peaks that pass a given point per unit time. All that means is if I had a clock here and this wavelength is passing through, I just want to know how many wave peaks, which are these points at the top, here, 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 and all the way down. I just want to know how many wave peaks will pass per a unit time. And those units are hertz or second inverse, which is just 1 seconds. By multiplying the wavelength of a wave by its frequency gives us the speed of the wave in meters per second. This constant is also known as the speed of light, defined as the rate of travel of all radiant energy in a vacuum, is equal to 3 times 10 to the 8th meters per second. The way that speed of light is calculated is by taking lambda, which is the upside down Y looking symbol, which is wavelength, multiplying it by the frequency, which is the Greek letter nu, almost looks like a V, and that will give us the speed of light. By looking at this equation, we can draw a conclusion that wavelengths and frequency are inversely proportional. That means that as wavelength increases, frequency decreases, and vice versa. And that will always be equal to the speed of light, 3 times 10 to the 8th meters per second. Now I'll move on to the next slide where we can work some problems. So the first question on the slide asks, what is the frequency of a microwave with a wavelength that is equal to 6.47 times 10 to the negative third meters? Our original equation is C equals lambda times nu, where C is speed of light, lambda is wavelength, and nu is frequency. So if we want to find frequency, we can divide both sides by the wavelength. This equation implies that C over wavelength is equal to frequency. Now if we take 3 times 10 to the 8th meters per second and we divide it by 6.47 times 10 to the negative third meters, we will get our frequency. I can rewrite the equation as 3 times 10 to the 8th meters per second, all divided by 6.47 times 10 to the negative third meters, and that will equal our frequency. This is equal to 4.64 times 10 to the 10th. And the units for frequency is hertz, or second inverse. One important thing to note here, if we have wavelengths, we want to make sure that the units are in meters, or else you'll need to convert. Or if we have frequency, we want to make sure that it's in hertz or second inverse. That way, these units and these units cancel, and you're left with seconds on the bottom, which is second inverse or hertz, or 1/2. The next question asks, which has the higher frequency? Infrared light or ultraviolet light? Which has the longer wavelength? Which has the highest energy? So one thing we haven't said anything about is energy. How is energy related to frequency and wavelength? We know that as wavelength increases, frequency decreases. And energy is directly proportional to frequency. So that means as one goes down, the other goes down. Let me repeat what I just said. As wavelength increases, frequency decreases and energy decreases. So this will also go down, or vice versa. Wavelength can decrease, frequency can increase, but that also means that the energy will increase. This means that frequency and energy are directly proportional, and frequency and wavelength are indirectly proportional. What we're looking for is the highest frequency, so I'm just going to use an arrow going up to show that it's the highest frequency. Then we're also looking for the longer wavelength. And we're also looking for the highest energy. Now we'll go back to the electromagnetic spectrum so we can take a look at it and find out the following answers. By looking at the electromagnetic spectrum, we see that frequency increases this way and wavelength gets longer in this direction, which means that they are inversely proportional. The question asked was between ultraviolet and infrared light. And the first thing I wanted to know was which had the longer wavelengths. And if we see here, we know that wavelength increases to the right. So that means that between ultraviolet and infrared, infrared will have the longer wavelength. So I'll just abbreviate infrared with an I. And then I wanted to know which one had the highest frequency. And if wavelength increases in this direction to the right, then frequency increases to the left. So that means that ultraviolet light will have the highest frequency. Now, energy is not given on this electromagnetic spectrum, but we know that frequency is directly proportional to energy. That means that as one increases, the other also increases proportionately. The highest energy will also be ultraviolet light. The next question asks, what is the wavelength in meters of ultraviolet light with the frequency equal to 4.52 times 10 to the 15th second inverse, or hertz? We know that speed of light is equal to lambda times frequency. If we wanted to find wavelength, we know that this equation implies that speed of light divided by frequency is equal to wavelength. 3 times 10 to the 8th meters per second, all divided by our frequency, which is 4.52 times 10 to the 15th hertz, or second inverse, or 1/2. We can calculate that on our calculator, and that will give us 6.64 times 10 to the -8 meters. And that is the wavelength of ultraviolet light with a frequency of 4.52 times 10 to the 15th. An important thing to note when doing these equations is to remember the fact that as wavelength goes up, frequency goes down. In this case, we see that we have 4.52 times 10 to the 15th. So to the 15th is a very large number. This means that the answer that we should get is something that is very small. If you're not sure if you got the correct answer, look at the difference between your wavelength and your frequency, and remember the proportionality between the two, and that can help you to kind of narrow down if you've gotten the answer right or not. So the next question is a bit of a tricky question. It asks, of the following, which form of radiant energy travels the fastest? If they're all forms of radiant energy, then they all have the same speed. And the speed is 3 times 10 to the 8th meters per second. So, of the following, which form of the radiant energy travels the fastest? None of them. Radio waves equals sound waves, which equals X-rays, which equals infrared rays. So I just wanted to make a point of that on this video because I've been asked that several times, and that's always been a trick question for people to understand. Remember that the speed of light is a constant. It never changes. So all of these forms of radiant energy travel at the same rate. That will be the end of this video of electromagnetic spectrum and how to calculate wavelength and frequency.